Hooke's law. Now, Hooke's law is also a required practical at GCSE. So we have to be familiar not only with the actual practical itself and the independent, dependent and control variables of the investigation, but also an equation to do with Hooke's law, and also how that leads on to a second equation to do with the elastic potential energy, but also to be able to explain it and look at secondary data to explain a graph that is formed when elastic objects follow Hooke's law. So Hooke's law was named after a scientist called Robert Hooke, and he was alive at the same time as Isaac Newton. Now, Hooke not only was a physicist, he was did a lot of work with astronomy and glowworms and geometry. He famously came up with the idea that snowflakes have that symmetrical shape. So Hooke's law states that the extension of a spring now this could be also a sort of an elastic object is directly proportional. Now, directly proportional is so key in this practical, but it's also key in all parts of your GCSE. So I'm going to underline it there, and actually I might highlight it as well because that's how important that term is. So it's directly proportional to the force applied. Now that is until the limit of proportionality is exceeded. Now, if you are writing some notes down, I suggest you write down what I have just written here, and then you can base some other notes around it. So until the limit of proportionality is exceeded. Now, the limit of proportionality, as it suggests, is the point where it no longer is proportional. So it's no longer directly proportional. Now we're going to look at a graph about what that looks like, but let's just go to the required practical, a practical that potentially you would have done, and it would look something like this, where you had a clamp stand, just here, there's your clamp stand, with a boss, and a clamp, and a spring over the boss. Now, for this practical here, you can see I put the bottom of the spring at the point where it hits 0 centimetres or 0 millimetres. Alright, so that's key when we do this. And then all you've done in the practical is that you added on these slotted masses, and each slotted mass causes the spring to extend, and when it extends we record the extension here. So you can see after one slotted mass, which is 100 grams, it's extended around about 25 millimetres, 2.5 centimetres. Now this is a good point here where we want to reduce error. So an exam question might be looking at the secondary data here, is how would you do that? Well, you want to make sure that actually that your eye level with what you're looking at here, so you can see it at eye level, so it's nice and straight. So this here is 100 grams. Now, this practical itself, we've got to convert that 100 grams into a force. Now, have a little think about how you would do that. Okay, so we're going to come back to that in a moment after we've looked at the practical equation. So here we have some further masses being added to the practical, and each time we've recorded the extension. So as I said, each of those slotted masses are 100 grams. Now, for the equation we want to look at for Hooke's law, it is force is equal to the spring constant times the extension. Now, the spring constant is basically how stiff the spring is. So the bigger the K, the stiffer it is. And the smaller the K, the less stiff. So car extension springs will have a large K. Force, we measure in newtons, extension in meters, and spring constant in newtons per meter. Remember, this gives us a clue to how we can rearrange this practical equation. So if we want to work out the spring constant, have a look at the equation here. We've got force divided by extension. So it's force divided by extension. The units give you a clue. Now the force, we said there, is in newtons. Okay, but we've got, which is a weight, we've got 100 grams, which is a mass. So we've got to use another equation. Remember, weight equals mass times gravitational field strength. So if our mass, we said there, is going to be 100 grams, that mass, however, needs to be in kilograms. So it's 0.1 kilograms times 10. We'll have gravitational field strength of 10. So that's just going to be equal to 1 Newton. So each of these masses here are 1 Newton. And each time we're measuring the extension. Now, one key mistake is that when pupils do this, they measure the whole spring each time from start to finish. All right, that's wrong. All we want to do is measure the extension of the spring after each Newton has come through. So you can see here what we've done here. We've got force and we've got extension, and we plotted that on a nice graph. And you can see the graph is directly proportional. That as we increase force, we increase extension, and it's proportional to each other. So if we double force, we double extension, and so on and so forth. Now, eventually, if I continued this graph will start to curve around. And it's this curvature here, when it starts to curve, where it no longer obeys Hooke's law. And we say that is the limit of proportionality. So that's the limit of proportionality, where it's no longer proportional. Now, eventually, if we keep stretching a spring, like this spring here, and keep stretching it and stretching it and stretching it, all right, it will no longer return to its original shape. So we say there that it's reached its elastic limit. Okay, and when it reaches the elastic limit, it will become inelastic. So Hooke's law, you might be asked to analyse some secondary data. So at what force does it reach the limit of proportionality? It might be you've got to use this data in the graph to work out K. So Hooke's law, remember, force equals K E. Remember, it's a required practical, and hopefully this video would help you explain what Hooke's law is. A later video will look at a bit more about elastic potential energy, so keep an eye out for that, and that's a further calculation there. But both of these calculations can be linked together in a multi-step calculation. So I hope that's helped you. Remember to subscribe, and we'll see some videos added a bit later on with some examples of these on. Good luck.